Okay, so yesterday we had you guys do a little investigation to learn a little bit about what's called standard form of a parabola. Now, if you do any research online, you'll find out that just like regular like lines have multiple forms, parabolas, there's different forms of a parabola that we use in math. And for right now, just as our beginning stages, we're going to deal with what's called standard form. So let's take a look at what that is and just remind ourselves how that plays out. So when you deal with standard form, that is any equation that looks like y equals ax squared plus bx plus c. So I have below a series of equations that are all written in standard form. Now, the further you go in math, we start naming things instead of saying everything is y. It would be sort of bummer if everybody had exactly the same name. So instead of calling this one y, I'm calling it f of x, but that's a fancy way of saying y. And this is g of x. Instead of calling it y, it's just a new one. So this is Fred and George. Here's Hector down here. But those are just different versions of saying y to somebody. So in this first problem, my a value is 1. My b value is -4, and my c value is 2. In my third example down, or actually it goes to the second one, my first is 1, a is 1, b is 6, and c is -1. Number 3, I wanted to put in there just to emphasize something, because you'll notice that the x term is missing. So what that would mean is if that term is missing, that would imply that it's a 0. So a would be -1, b would be 0, and c would be 5. So again, it's very, very simple. We always arrange it in order with the biggest exponents first coming down. And so a is the coefficient sitting on the x squared term, b is the coefficient on the x term, and c is the constant that's sitting at the end. Now, what you learned in the activity that we did yesterday, a is kind of important because it tells us how steep the graph is and also whether the graph opens up or opens down. C told us the y-intercept, which effectively slides the graph up and down a little bit. And B was kind of a weird one where it kind of moves it left and right, but it also kind of moves it up and down a little bit because it had to pivot around this value C. So what I wanted to do is take you through a couple of examples that remind us what we did yesterday. And I have those actually sitting right in here. Sorry, I had something else up for another class. But my first question here, Q1, you would notice that this thing has it should be opening up and it should have a y-intercept of 2. And so when we see it, there it is. It hits the y-axis at 2. The second problem, you can notice, also should open up and it should have a y-intercept of -1. And we can see that right there. So one of the things, though, that you'll notice if we were to turn both of these things on is that they're not the same graph. You'll notice that this one turns around. This is actually known as the vertex, although sometimes we will call it a locator point. This one has a vertex of 2, -2. This one over here has a vertex of -3, -10. And they really actually have very much the same shape. They've just been moved over from each other. So they're actually, just like in geometry, those are congruent parabolas. They're exactly the same parabola. They've just been moved to different places. And so what we really need to learn how to do is find that locator point. And so that's the purpose of this video today, is to learn how to find that locator point from vertex form. So let's go back to the document cam and let's learn how to actually deal with that. So the first thing that we always want to do in finding that is we go to a little equation, which is x equals opposite b over 2a. Some of the reasons for that are going to come at a little bit of a later time. But for right now, if you just believe me that that's an important formula, that's going to be pretty good. So in this particular case, remember b was -4, so the opposite of b would be +4. And then I'm supposed to divide that by 2a, which would be, of course, 2 times 1, which is 2. So that gives me an x value of 2. Now, as it turns out, that is the x component of the vertex. It's also what is called the axis of symmetry. And so we have some pretty important little pieces of data about this graph. Now, the next thing that we need to do is we need to plug that number 2 back into the original problem. So if we plug the number 2 in, what I'm going to do is I'm going to take each of the x values in the original problem, and I'm going to replace those numbers with the number 2. I'm going to put a 2 here and here that line up with the number that I got when I did opposite b over 2a. So keep in mind that's going to change with each problem depending on that value. Now, when we do 2 squared, of course, that's 4. And 4 times 2 is minus 8. And we add that 2. And I just got a grand total of 4. Minus 8 is negative 4. Plus 2 is negative 2. And you might recall that that's the vertex that we found on that previous problem. Now I'm going to highlight this in green because I want to kind of come back and mention something about that when I get a little bit deeper into there. So let's take a look at this next problem. Again, x is opposite b, and opposite b would be minus 6 over 2a. And so this particular one would have an axis of symmetry at x equals negative 3, and its vertex would be at negative 3 comma something. But we need to plug that back in. Now, notice that this function was called George, or G, and so I'm going to plug negative 3 into that original problem. So I've got x squared plus 6x minus 1. So we're going to replace the x values with negative 3. And we got a 9 right here, a negative 18 right there, and a minus 1 for a grand total of negative 10. So my vertex is at negative 3. Negative 10. Now, as I mentioned before, I want to go ahead and draw your attention to what is happening right here in this part that I'm highlighting in green. I always love it if there's things in the problem that can tell me if I'm on the right track and that I've done good work. And one thing that you're going to see right away in this problem is, you see how this number is 4 and that one's negative 8? These are always going to be in such that if you have done it right, the second number is actually twice as big as the first number, and it's the opposite sign. So notice 4 doubled is 8, and it's negative 8. 9 doubled is 18, and it's negative 18. So we will see that throughout these problems that we go through right here. So I wanted to just make sure that I'm as thorough as possible. So in number 3, when we did opposite b over 2a, it's not a big deal, but what we have is the opposite of b. In this case, there was no b value, so we said that was going to be 0 over 2 times negative 1. So it looks to me like my axis of symmetry is at x equals 0. The vertex is at that 0 value, and of course, if we plug in 0 squared and then we add 5, keep in mind that each time whatever we plugged in, we plug that in for x. And in this case, I've got 0 squared is 0 plus 5 is 5. And notice we don't have that little green thing because if we double 0, we still have 0. So that little piece wasn't there. And so now I have a vertex of 0, 5. Now, when you look at a problem like this, I know a lot of people would be a little bit frightened by it because the numbers are just so large. But again, opposite b over 2a would give me negative 4. So let's see if our little trick worked here, and that if we go ahead and we plug that number negative 4 in, if we in fact do continue to get that pattern that we've discussed. So I'm going to plug that negative 4 right here, and notice that we changed x to negative 4 in each case. So negative 4 here and here. Let's see, order of operation says we better square the negative 4 first. So negative 4 squared is 16, and 16 times 3 is 4. And what do you know? We have exactly what we were hoping for. Now, if we take 48 minus 96 plus 42, that whole thing comes out to negative 6. My vertex is at negative 4. When I plug it back in, I got negative 6. And not to beat this up too much, I did want to do one of these problems where you're going to notice my A value is negative. So this particular parabola is going to open down. It's going to have a y-intercept of -10. And so when we do opposite over 2a, in this case, I got -8 over -4, which is +2. So each of the other problems had something a little bit different happen, but notice we got a double negative here. And we will continue to see the nice little pattern. Again, this is the way I do problems. I always take the x value and I leave it as a blank, and then after I'm done writing it in parentheses to watch my order of operations, I put those values in. And so I have a -8 here, a +16, and notice it fits very, very nicely for us as we go through that process. And it looks like to me I've got a -2 as my vertex. So I plugged in 2, I've got -2. Now, I'm going to have this sitting in front of me, but I want to go back to that Desmos real quick and take a look and make sure that the work that I have done is correct. And I think that's always really an important thing to do as you're doing your own mathematics, to check your process and make sure that you have not made mistakes. So moving back in here to Desmos, here is my first question that I had that we talked about a moment ago. And what you'll notice is that when I plugged in the number 2 into the equation, notice we got -2, and we can see that beautiful little thing that is sitting there. And in fact, I'm going to do one more thing, and I'm going to type in x equals 2. That's called that axis of symmetry. And you can see that nice dividing line that cuts that thing in half. And so you can see how perfectly symmetric it is about that nice little dotted blue line. The second problem that we had, number 2 right here, we found a moment ago that when we plugged in the number, I think we got -3. So look what happens if I say, hey, calculator, can you tell me what -3 is? And it says, hey, your vertex is down here at -3, -10, which is exactly what we thought it was. And I can turn that graph on and you can see that nice pretty symmetry that it has. And here is my axis of symmetry going x equals -3. Remember, it's that x component. And it looks perfect. And you can also see that it hits the y-axis at -1 like we do. So that gives you a little bit of a start. Now, if you can ever find the vertex, in the next video, we're going to tell you exactly what you can do to take that vertex and go further through the process and actually finish the rest of it. But the key is you need to know what that axis of symmetry is, and you also need to know exactly where that vertex is on that axis of symmetry, and then it's super easy. It's no harder than graphing a line. So I hope this was a helpful video for you. Make sure that you watch the next one or you won't be able to finish the assignment, but I think it's pretty straightforward. Okay, let us know if you have trouble.